started. Welcome, everybody. Welcome to OpenCV Weekly Webinar. And today we have Joseph Nelson again on this webinar, giving us a lot of knowledge and information about a technique called active learning, which he will describe. Welcome, Joseph.
Thanks. I appreciate you all having me. As I like to say, the mistake of inviting me back. So we'll have another good time.
Oh, your webinars, whenever you have been, they have been very, very popular. People love it. So welcome back.
It's a ton of fun. Thanks for having me.
Definitely been consistently some of the highest rated ones for some ungodly reason.
Appreciate it.
We also have Phil Nelson, who is the content manager at OpenCV, and the two Nelsons are not related.
Like Buster and Babs Bunny, we are no relation.
Great. So, Phil, do you want to announce, our standard giveaway?
Yeah. So, if this is your first time, we'll be doing a giveaway at the end of the webinar. Satya, would you like to tell them what they'll win if they answer the trivia question correctly?
Well, we can do a few things. We could do, the thing in the box, but you'll have to wait for it. Alternatively, we could also do. Joseph can throw in, a little package for somebody who wins the trivia question,
or possibly a live raccoon.
That's true.
We do have our standard giveaway for those that get the trivia question correct, which includes some great Roboflow swag. So more on that towards the end.
All right. Sounds great. We'll also be doing live Q&A with people in the audience here. So please use the Zoom Q&A functionality to ask your questions at any point during the webinar, and we'll do our best to answer as many as we can at the end.
All right. So let's get started with active learning. Joseph, please share your screen and we can get started.
Sounds great. Thanks all. Let me provide a little bit of an intro about Roboflow to give some context. And I'll introduce OpenCV as well, and Satya ask you to voice over. And then we'll dive into substantively active learning, why it matters, and how it improves your models more quickly. At a high level, at Roboflow, we're all about empowering software developers, engineers, data scientists to use computer vision more effectively. To date, a little over 50,000 developers have built with Roboflow. And as computer vision is a technology that's broadly applicable, we've seen some pretty fun use cases. So I've bolded a few here just to highlight and call some of those out. Some of those on the commercial side, for example, like crude oil release detection or detection of environmental factors. We've seen teams in agriculture identify where weeds are or do yield predictions. We've seen teams in the construction industry identify and confirm that PPE and hard hat construction sites are correct. We've seen a number of companies in manufacturing that do visual quality assurance, ensure that the devices and widgets that they're producing are up to the standard that they expect, which is, as you can imagine, a very visually intensive task. We've also had a lot of hobbyists, students, and those that are toying around build some wonderful capabilities too. One of the ones I like to talk about, you'll see it bolded here, is Sushi Detector. And that project, if you're unaware, if you've grown up in the Western Hemisphere, your digestive system has grown in a specific way that if you have something that's common in the Eastern Hemisphere, for example, let's say you're visiting Tokyo and you have white tuna, it can actually make you quite sick. And so we had a Roboflow developer that built a product that identified if a given type of sushi contained white fish, right? So if you're on your trip in Japan, you could see and be sure that you eat food that doesn't upset your digestive system. And all sorts of other fun use cases that we'll talk about today. Things for making gardens safer from rabbits, board game detector, things for making board games more fun to play, which are near and dear to my heart, of like making it easier to identify the state of a chessboard, all sorts of wonderful applications. And the way through which we empower those types of applications is through our tooling. And so, as I mentioned, there's a number of commercial partners that work with Roboflow across the Fortune 500, just as much as there are a lot of individual developers. Companies like Walmart, United States Gypsum Corporation, Cardinal Health, and smaller companies as well. So a number of questions we get from the commercial and enterprise side is ensuring that having an enterprise ready product that's ready to scale, ready to support large workloads, secure, and all of those things are places where we're certainly intimately familiar. The way in which we do that capability is we'll talk about in greater depth, but I do want to give Satya the opportunity to introduce OpenCV at a high level as well.
Great. So yes, this webinar will also be shared with the Roboflow audience and people who do not know. OpenCV is the biggest computer vision library in the world. It has been around for 20 plus years, and it has about 2,500 different algorithms implemented in it, and it gets downloaded about 1 million times a week. So it's very popular. People use it in conjunction with other popular libraries like PyTorch and TensorFlow. And we also have a hardware called OpenCV AI Kit, which is a smart camera which can do neural inference, as well as depth estimation in real time. And we are running a competition right now. It's the second phase. We are right now running OpenCV AI competition. People have already submitted, so we are just waiting for the finals for this. And I just brought it up because, Joseph, I noticed that several people in several participants in the competition actually used Roboflow to train their models. So it was a nice surprise because Roboflow is also a silver member of OpenCV. So thanks for the support as well.
Absolutely. Yeah. We're all about empowerment of developers. And that kind of brings us to the point of why it is that we partner together. So some of the things that we worked on include things like this webinar of bringing educational content. At Roboflow, we're all about increasing accessibility and use and broad adoption of computer vision in a very open way. And so through educational content on our blog, through video content on our YouTube channel, and through partner webinars like this, we view that as pretty integral to our mission. Other ways that we work together with OpenCV include creating and deploying the easiest way to deploy to the OpenCV AI kit. So Luxonis, who produces the kit, OpenCV, and Roboflow have partnered and created the ability for seamless deployment for any custom trained model directly to OpenCV AI kit, or OAK, as we often say. And as Satya mentioned, we've seen some amazing use cases built, things that empower accessibility, things that enable, for example, we saw someone that made a retail store detection. They actually mocked up an entire environment in Unity and then used the OpenCV AI kit and Roboflow to identify if certain goods were missing from shelves, or if something was low stock or placed in the wrong spot, or a price match was incorrect, or things like this. So it's been a really nice partnership in terms of making it even easier for folks to get started with computer vision. And as the OpenCV team has teased, there is something upcoming on Kickstarter. I'll keep my mouth shut on this point.
You better.
The subject of today's discussion is focusing on active learning. And before we dive into active learning examples, it's important to lay out the overall process by which computer vision solutions are built. And in the process of building those computer vision solutions, we'll see why active learning is so critical to building higher quality models faster. When you use active learning successfully, you have a model that gets to production faster, that is more accurate, that requires less data to be able to get there, and is an overall easier experience to incorporate into your overall application. So if active learning is so great, how do you get started and what's required? In general, when you build a computer vision model, of course, you need to have images or video collected. And that's kind of like the first step, making sure you have a healthy data set of places to get started. A common question is like, how many images do I need and things like that? And generally what we like to say is enough to have an initial model. And some folks kind of get stuck on, you can actually collect an infinite number of images. In other words, you can almost never have too many. So often the question is, how do you get a sufficient number to get started with your problem? A few thousand, a few hundred. It really depends on the problem that's being tackled. But the big point is not to get too bogged down with needing hundreds of thousands or millions of images before you can make an impact. Because especially as models improve, and through augmentation, you can actually get to an initial model pretty quickly. Now, once you have an initial data set collected, there's questions around which ones should you annotate, which images should you draw bounding boxes on, or segmentation or classification for the purposes of improving your model. And this is where you begin to organize and label the data set, perhaps with you, perhaps with third-party services like Mechanical Turk, perhaps with members of your team. We've seen folks use Upwork pretty successfully as well for getting annotation needs completed. And once you have your data set collected, organized, and labeled, you'll train a model. And there's a number of different models to try, of course, just as much as there is an understanding of model performance. Now, one thing that I really encourage folks to think about as you build your model is think about it like data-centric AI rather than model-centric AI. In other words, a lot of the times your model is useful as a way to benchmark your data set quality, not the other way around. So in other words, if you held your model constant, like you use the same model architecture and you try it on a couple of different data set variations, that often provides you with a greater set of information and knowledge of what you should do next to improve the model's performance. Maybe counterintuitively, having a model held constant and focusing on which more data you need is going to be much faster for getting to production solution. And we'll talk about like how that works and why that's true when we talk more about active learning.
Right. And you're also very, because you're selecting what you're putting in the data set, it's still a black box, but not as much of a black box, right? You could say that, okay, this is how we trained the model. So it does help quite a bit to know that, these were the weaknesses of the model, and then we corrected it using this additional data.
And the model, once trained for a first time, we then will deploy that model into production. Now, where we deploy it and how we use it really depends on the problem that we're solving. If we're running perhaps let's say we're eBay, and we're running a service where we're identifying if a given image is a good description of a given product, right? So let's say you're listing on eBay old shoes. Well, you might want to be able to see if the user uploaded images of shoes and maybe even the color of those shoes and things like this. And so in this case, we might have a web-hosted model where we know the user has internet because they're uploading to eBay and they're adding the images. And so they would use probably a web-hosted inference API. What's cool about computer vision is there's also a lot of use cases where you might be deploying out into the field as well. And you might have a model that needs to run semi-offline or maybe completely offline. For example, we've seen users with Roboflow build models that help people that are on Safari. So if you've ever been on Safari, I haven't, but I've wanted to. We have a partner that in South Africa, they've built a model for folks that are out in the bush that want to point their devices at animals they're seeing and almost get like Wikipedia-like information about those animals. Cell phone service is not particularly strong in these areas. And so being able to have a model that runs offline and brings up information once it recognizes these animals out in Safari is important. Or maybe you have a model that's running where people aren't at all. Maybe a model that's doing detections and inference on maybe security camera footage or looking for open spaces in a parking lot. All these sorts of things are places where you may want to run something at the edge. And this is where deploying to things like the OpenCV AI kit can make a big difference because you can run your model completely offline in tandem with the video feed as it comes in. Now, this is where people often think, okay, great, I'm done. I've got my model, it's in production, and I'm good to go. Wrong. This is one of the biggest misconceptions that we see in computer vision. And that is, in fact, when you first get your model deployed, the next question becomes, how do you continue to improve it? Maybe add new classes, increase the scope of what your model is capable of telling you. And this is where not just displaying results of how the model is doing comes into play, but how do you continue to sample data from your production conditions to continuously improve your model over time. Your model might get to a point where you're sufficiently happy with performance for some classes, but even getting there is where you're going to want to think about the logic of how your model continues to sample data from where it's deployed. And that's where we're going to focus a lot of today's conversation on. And notably, the paradigm shift that I encourage you to think about is that instead of making the burden and the very first step of data collection being perfect, like you need every single example and every different permutation of an example, things could be brighter, things could be darker, things could be nearer, things could be further. Instead, have a data set that is sufficient to get an initial model in production, and then start to sample from your production conditions. And building with this in mind is far more resilient, faster, and going to save you lots of time and costs down the line. And so we'll talk about how that kind of looks in a couple of real world examples. And this is where active learning makes a big difference. So again, go ahead.
Go ahead. Sorry.
Oh, I was just going to say, emphasize what active learning is. Again, so active learning is the practice of taking an active role, an active approach in the data set curation and model improvement based on that data to enable getting to production faster. Right. Maybe a really one final like intuitive way to grasp this idea is, let's say we're doing the eBay shoe example. Let's say our model is working perfectly on tennis shoes and sneakers, but it's working quite poorly on women's heels. If you have a model that's working well on tennis shoes and poorly on heels, and you feed the model more data of tennis shoes, we can't expect the model to make pretty big improvements in the places where it's failing most, if it's failing on women's heels, right? And so an active learning approach would say, let's actually focus on where the model is failing. In this case, collecting additional images of heels to improve the model's capability to perform better on that class. And it might not just be heels. It might be images that are brighter or darker, nearer or further, different attributes about the image, or about the subjects that we're trying to understand. And so in the long run, active learning allows models to be much better, much more robust, and get to production much more quickly. Go ahead, Satya.
And things change over time. You know, one example is where active learning, if you're just starting out, right, you may, even if you do something simple as people detector, and when you're starting out, you may just, use a standard model from the web. And you'll discover that, when it is winter time during, it will stop working because people are wearing very heavy jackets, especially in, countries where people wear these very heavy jackets with a hood on where you can barely, see the face, etc. So that's one case where temporarily, right, over time, the data actually has the production environment has changed if you're not careful. You can also imagine such things happening in, let's say, an ocean. You build something, counting, like fish counting thing in an ocean, and the inside the ocean, you find that, the color of water, perceived color of water changes, or there is more turbidity, etc. So all those cases can change. Things change over time, and we have to have this loop so that we keep up with changing times. Another example would be, new class gets added, like suppose you have a make and model recognition engine that needs to be updated frequently. Tesla releases a new model, and now you have to add that in your training.
Those are great examples. Great examples. I mean, it's not just, there's both maybe the target class we have in mind. We want to get better on that target class. The conditions themselves could change. We might want to add new classes to the model. We want to expand the scope of what the model is capable of doing. These are all areas where you're going to want to collect additional data, and you're going to want to improve it. And I think the big paradigm shift this might encourage in machine learning and in model development is that instead of thinking, I need exactly 90 mean average precision before I go to production, or I need exactly 80. Actually, that question should be framed relative to the problem that you're solving. At what point does the model begin to add value to your process, right, and then inching it up over time? So if you're facing like an operational problem, let's take the eBay example again, right? Let's pretend like eBay has an army of manual reviewers that are making sure that images match the description of the items that are being listed. Computer vision would offer an operational improvement in this case. So if we have a model that maybe it only does, I don't know, 70% well on one type of good, and we'll say that's shoes, and we'll say there happens to be a lot of shoes that are being sold on eBay. Even though that model has a relatively small scope and room for improvement, we could already measure the operational improvement that model would bring to eBay's process, because it would allow, at least in that one category, a 70% improvement of shoes. And so getting that first model to production means we would start to see a return on our investment, not to mention the process by which we are now using computer vision, not just for that category, but for other categories, is unlocked and easier going forward. And so often thinking about things as stepwise improvements, especially in operational capacities, allows us to realize the value much more quickly.
That's true. And it's funny that in some cases, in some evil cases, even a small percentage, you could be right only a very small percentage of times and be fine. For example, if you're trying to break the visual captcha, right, and create some fake accounts, you could be right 1% of the time, and that's fine. Because it's an automated system, you could be creating a lot of fake accounts based on a very inefficient model, right? It's still useful. But you can think about some positive scenarios also. It just came to my mind.
Yeah. That is a good example of like any small breakthrough would contribute to the business problem being solved. Maybe we could talk through a couple of examples as well. So I have a few pulled up here that might be interesting to talk through. So one is an example that I like to talk through is pretend we're building a system for package detection, right? So let's pretend like you want to receive a message, maybe an email or a text message, whenever there's a package outside of your home. Now, these packages come in many different shapes and sizes. You may have this standard cardboard box like you see here. You might have white cardboard boxes from USPS. You might have the flat packs, like these white puffy ones, or these flat packs like these yellow ones. And these are all kind of different types of packages that could show up at your door. And moreover, maybe you're building a system not just for your door, but for multiple environments, right? So maybe you're building it not just for your apartment building, like the one in these three images. Maybe you're also building a system that's going to work for your friend's home, where the angle, the lighting, the camera position is a little bit different. And so these types of variations will introduce considerations of how to build a model that successfully is able to detect when and what type of package you have for the purposes of sending you a message. Now, if you're solving this problem, you could say, okay, my problem statement is I want to receive a text message of which package has arrived for me when that package has arrived. Now, when you go to the dataset collection step, you likely are going to want to be aware of thinking through, okay, how do I make sure I get some amount of my images of each of these package types? And you might build an initial model with some of these packages in mind. But you should be asking yourself, okay, which of these first ones, let's say 1,000 images, which of these first images do I want to label? And, logically, instead of saying that maybe I need to label all 1,000, you could maybe label a first 100 or a first 200, build a model and see how does that model do on, let's say, our three classes: cardboard boxes, white boxes, and flat packs, just for the sake of simplicity. And you might see, the model's already doing a great job on cardboard boxes and white boxes, but flat packs are where I'm kind of failing. So now, instead of going back and blindly continuing, or naively, I should say, labeling just a bunch more images, we can make informed decisions where we can use the model that we just trained to help us sift through the images that we have yet to label. And wherever the model might be giving either incorrect predictions or low confidence predictions are where we're going to want to focus our continued effort to improve and curate our data set. Something that's really important in this paradigm shift I just introduced is, yes, you have a high volume of data available initially, And yes, you might want to make use of all of that data over time. But instead of thinking like development as a waterfall cycle, this is kind of thinking about machine learning as an agile cycle, where we do one step, and once we have a sufficient progress on that one step, we try the next step. And that informs how we go back or if we go forward. Now, we can talk a bit about the types of active learning that allow us to do the types of selections of these data sets. But the initial idea that I want to introduce here is the conditions under which you might want to use active learning for data set curation, let alone model production.
Joseph, could you zoom into the post? It's very narrow on the screen.
Yeah. Thank you for calling that out.
Yeah.
So we have these 3 images.
Can hardly see the packages.
And the model would struggle too. Yeah. And so some conditions where active learning helps us combat are things like underrepresented classes, a varied set of image conditions, a diversity of classes that we're trying to understand. These are all cases where you should start to think, maybe active learning can help quite a bit. One other quick note I want to make is active learning and annotation can often work hand in hand, in that the more specific your annotations are, the more specific you may know where you want to do active learning. So for example, if we do annotation as just package, it'd be a little bit tough to see what types of packages our model is doing poorly on. Whereas if we do white package, or excuse me, cardboard box, white box, flat pack, that would actually help us see our model's breakdown by class type. And it would inform, flat packs are where model performance is doing more poorly.
So some additional effort upfront is going to be very informative later on. Otherwise, we'll be just having that data upfront would really help.
Certainly. And by the way, this is not purely theoretical. This package's data set is totally available and out in the open. This is a relatively small data set to get started, just 62 images with 94 annotations of package. But it's not purely theoretical of what we're talking about here. Now, I actually want to show some examples of, what we just talked about was active learning for the purposes of improved data set curation. But another way that I want to talk about active learning is the way it can flip the script in terms of how we build our model. Okay, so what we just talked about was the model building process, right? And we said start with collection, then do labeling, then train, then deploy. In fact, in some cases, you can actually start at the deploy step or start with a model that works by default. And ways that you can start with a model that works by default is there's both, increasingly, there are pre-trained models for given domain problems that you can start working from. So for example, OpenCV has model place, which has an example of some of these models. And within Roboflow, there's also users that are posting models that are available to get started with. So maybe I can show both of these examples. So model place, maybe I'll do this, model place.ai is one example of where there's a number of off-the-shelf models where you could try for backpack detection or things of that nature from the OpenCV ecosystem. And they're ready to run on devices that you might want to run them on, and all these sorts of capabilities. There's also, in the example I kind of want to show as well, Roboflow Universe. And so Universe is where, in the same way that GitHub has made open source code be a really forward and move the field forward, Universe is doing the same thing for data sets and models, and for developers to basically jumpstart and get a kickstart of how to do computer vision, both with starting with a pre-trained model in mind or starting with a data set in mind. And it's basically us at Roboflow saying, we've had 50,000 developers build with us. Many of those are developers that are moving the field forward. With our tooling, we can empower that community of developers to collaborate out in the open and both giving themselves credit. So for example, some of these data sets are curated by folks like Augmented Startups, a YouTube channel with 90,000 subscribers, or Streamlit, a company that makes tools for deploying models, or General Dynamics, which is a defense contractor. And they can kind of contribute data sets and models to move the field forward. And we at Roboflow can use our tooling and community to enable those connections to happen so people can get to production faster. How does this relate to active learning? Well, remember how we said, often you want to start with data set collection. Let's pretend like you want to build a model for raccoon detection, which is a problem that is near and dear to us at Roboflow for a variety of reasons, and maybe related to the swag that we're going to talk about later today. With raccoon detection, let's pretend like you want to find if there's ever a raccoon. You might have a raccoon that's like running around in your trash, or it's a pesky raccoon, and you swear it's there, but it's never there when you say it is. And so you set up a camera and you want to capture when the raccoon is there, and then you can perhaps then convince animal control to come help you out and humanely remove it from wherever your suburban home is in this example. But first things first, you need to prove that there is a raccoon there, but you don't want to stay up all night watching it. So you build a little model and you're like, okay, I want a model to detect raccoons. Well, instead of saying, hey, I need to go immediately have a data set collected of all my raccoons, you could come here in the Roboflow universe and you would be in luck. We have a raccoon model that's ready to go. So I'm going to go here and click use my webcam. And this will load the model to run immediately in my browser. I may need to turn off my Zoom so that the camera can switch the input feed. But this model, which has been already trained, is one that I can use directly in my application, whether I'm going to use it via API or I'm going to use it, there we go, or I'm going to use it on my Oak, wherever I want to use it. And just as you guessed, I have a nice raccoon crossing sign handy, just in case for instances like this.
Nice.
Very brave live demo.
And something I want to highlight here is notice that the raccoon model does fail at times. So for example, if it's only partially visible, see here with this amount of occlusion, the model's not sure this is a raccoon. Or I can put the sign at a pretty steep angle in the glare. See if I can get the model. This model's pretty good.
You trained it really well.
If I get it at this steep angle, if there's a really flat raccoon that's in your yard, it looks like the model would start to fail here. And actually, I know that this model fails if I get pretty far away.
Yeah.
So very small raccoons. So I could go ahead and jumpstart my process of active learning, where now if I incorporate that model directly into my application, I could then start to sample on where the model is failing and start to focus my efforts on only getting data where my model needs to improve. And let me do this. Come back on camera. There we go. So in other words, we saw that the raccoon model by default does sufficiently well to start using to look for raccoons. But there might be some cases where the model is failing. And what we're interested in is surfacing those cases so that we can go back to the beginning of our process and do collection, annotation, and improvement. Now, what's critical, by starting with a pre-trained model, our efforts leapfrog so we can start with saying, okay, where is our model actually failing? Which brings us to the next thing that's important to discuss, which is how to sample when the model is failing in production use cases. So this is a key part of the active learning process that's worth discussing in greater depth. So to recap, what we just described is if you can start from a model that isn't perfect, but is sufficiently good, the question becomes, how do I incorporate into my end application the ability to sample images where my model is most likely failing? And so this begs the question of which failure conditions exist and how we build in tolerance for those types of failure conditions. So Satya, I'll let you kind of brainstorm some ideas with me here. Like, what do you think are some cases where our model could be failing?
In this raccoon case?
Yeah, or in the general case, either one.
Yeah, so I mean, you could imagine that we have not sampled the classes uniformly, right? There are some classes where there is not sufficient examples, right? That's a classic case, happens all the
Totally.
time. And then there are there could be other biases, depending on how you collected the data. You could have even we talk about racial bias and all those things, but even in very simple cases you can have bias. For example, you could be looking at like the packages, for example, right? You could have collected all brown packages and a pink package comes in and it's not there, right? So it's
only boxes and none of the padded mailers, for example.
Yeah.
Yeah, I totally agree. So yeah, so I mean, one key condition could be underrepresented classes, classes where we don't have sufficient representation, even of the classes that we have in mind. And so if we break down our model failure types, we might have examples where, for example, you might have a false positive case where a model makes a prediction, but there isn't actually anything there. When I first brought up the raccoon model, there were a couple of flashes of false positives that you might have saw, like thought maybe there was a raccoon in my bookcase, which I hope there's not. So there's some false positive cases we might want to look for. And then there's...
I mean, of all people, they would have reason to want to, just keep an eye on you specifically. You do keep an eye on them.
Yeah. The raccoons are probably on to me. You're right. But at least more training data. So yeah, so we might have a false positive example, right? Where the model's making a prediction, but it's incorrect. And it might be making a prediction where there's nothing there, or maybe it's predicting dog when in fact it was a raccoon in a multi-class case.
Right.
We might have failure cases where the model is failing to make a prediction at all. So a false negative, right? Where there was a raccoon in view, like when I went too far away and we could see the raccoon with our eyes, but the model was failing to see it with the model's eyes, if you will. So we have this false negative case as well. And then even actually, we might have cases where we have true positive, where we're happy that the model's finding the raccoon, but it should be doing it with a higher confidence level. And so this is a key thing within active learning in general, is that you get to dictate the confidence level at which you consider the model to be finding our subject of interest. If we have the confidence level set very low, like, hey, show me any prediction that you're more than 10% confident, we're probably going to get a higher rate of false positives, but we are going to find more of the raccoons as well. If we have a confidence level that's very high, 90, 95, 98% confident, then we might miss some of the more obscure raccoons, but we'll find the really obvious ones. And when we find a raccoon, we'll be absolutely sure that it's a raccoon. So that confidence level allows us to kind of fine tune how sensitive our model is in making these predictions. Now,
yes, it may not be very robust. I mean, something that is hovering at 50%, in a binary classification, and you just get over 50% slightly, even though, your model may look, oh, it's producing good results, but it's kind of fragile, right? Because it's hovering right near that 50% mark. What we want it to be is in the high. You should do these, add additional data to separate the two classes. And one example of this, I think I've mentioned it before also in some other webinar, is huskies and what's that? Jackals? Huskies are similar to wolves, right? They are very similar in appearance, and so to tell them apart, you have to use a lot more data. So you could also come up, you may think that, oh, I have so many images of these two classes, but if the classes are kind of close to each other, you need much more data to tell them apart, right? So those kinds of things will also affect which classes are important.
Yep. Yeah. And so, I mean, if we think about an active learning solution, we might deploy an initial model where we have the confidence level set lower, but over time, our goal is to bring that confidence level higher and higher as we select and collect more data. So that brings us to this question of, okay, if we have those types of failure cases, we have true positives, which, we're actually happy with that, but the confidence level isn't high enough for our standard. We have that case. We have the case of a false positive where the model is making a prediction, but the predicted label that it's showing is incorrect. So it's a husky instead of a wolf, for example. Or we have a false negative where the model's not seeing the object of interest in frame. Now, these are cases where we're going to want to use active learning. And based on the application we're building, depends on how much quality assurance and how much we can rely on our users to select these failure cases for us. Now, let's start with the failure case where the confidence level is, let's say we only want to say there's a raccoon when we're 80% confident. And the model is finding raccoons at 60% confidence, for example. Well, in this case, we could have our model deployed in production. And whenever the model is making a prediction that's lower than 80% confidence, we can store that image, cache it, and then send it back to our source data set when there's internet connectivity. And maybe we have an internet connected app so we can do it instantaneously. But the key idea here is I have my model running in production. As my model's running, I'm going to be receiving confidence levels of raccoon predictions. If I ever have a prediction where the confidence level is lower than the threshold that I am interested in setting for my application, I almost freeze frame, grab that image, and send it back to my source data set. And so we'll talk about how to implement something like that. But that's kind of the first case. A second case may be if the model is making a prediction, but it's the wrong prediction. This one is trickier to catch without a human in the loop. But in some applications, maybe we actually have our users that are the human in the loop. Return to the eBay use case where we have tennis shoes versus heels. If we have a user that is saying, yep, these are tennis shoes, and you've correctly classified that based on my upload, then we actually have the ability to solicit human in the loop feedback directly from our users, which is highly scalable. Right. We may have some cases where we're not able to solicit directly from our users. And so in these cases, it will require some manual curation. And then the last case of false negatives is very similar. It's probably one of the trickiest to debug because trying to find the case of when an image is, or when an object is present and the model didn't think it was present can be tricky. And it does require some human in the loop process to do that. So for these cases, actually, sometimes what I recommend is if you set a confidence level extremely low on your model and then surface, yes, a lot of false positives, but you'll probably also find some of those cases where the model might have otherwise missed. And as a last note, in addition to doing sampling, intelligent sampling based on confidence levels from your production conditions, you may also want to just have like a fail-safe, like random sample. In other words, like send back every 10th prediction and send back those 10th predictions or 10th frames without prediction, depending on the context that you're working in, so that you just continue to curate a data set once your model is in production. This is the secret to getting models to production faster and more accurately, is continuing to build with production sampling in mind.
Right. One example, you mentioned that you can get your users to help you out, and that is scalable. And a lot of people may be thinking that, oh, I'm never going to do that. I'm never going to actually put in the effort to do that. But in fact, every one of us, 100% of us have actually helped do it. When you actually solve reCAPTCHA, you see two words. One of the word is known, the other one is actually not known. They don't know for 100% what exactly that word is. And when you fill it out and multiple people fill it out, they know what it is. And then, that is used for training text recognition engines.
Yeah, that's one of the earliest examples I can think of a company really, they basically were one of the most visible kind of machine learning startups, 10 years ago.
Right. So a lot of that data was going back to train, text recognition, especially scanning of books and things like that.
Let's talk about implementing one of these active learning techniques. So we talked about conceptually the ways of sampling from our inference conditions, but what does that actually look like in practice? The way I want to talk about this is actually a project that a Roboflow Summer intern, Samrat Sahu, built a project that is quite fun and quite inspiring. So Samrat, who recorded a full YouTube video of the overall walkthrough process, which we'll be sure to include in follow-ups, created a model that scared bunnies out of his garden. Okay, so Samrat had this problem, and he's planting things in his backyard, and the rabbits kept eating his vegetation before it was able to get mature, and it was very frustrating for him. And instead of wanting to do, I don't know, like a fence or electric fence or something like this, he thought, what a great way that I could use computer vision to see when there's a bunny in view of a place that I don't want there to be, and then use a Bluetooth speaker to play a startling noise to make the bunny run away. And you can see from this GIF here, the noise is playing. I don't think you want to hear the annoying noise, to be clear. So we're lucky that it's a GIF. But the noise plays and the bunny runs away. Now, you might be wondering, what noises did he play? And I will spoil it for you. You can watch the YouTube, but I'll spoil it. There were two noises that he played. One was a baby crying, and the second was the noise of like a car driving by. And so I kind of joked with Samrat. I was like, this is a phenomenal project, but maybe you're just conditioning bunnies to be okay with the noise of cars and the sounds of like young children crying. But we'll have a follow-up in a couple of years of have the bunnies learn to be adaptive to these noises.
I was also wondering what the neighbors might think when they just hear like a random crying baby and can't locate it, or
I have the exact same problem. Watermelon. So for the first time, I planted watermelon in my backyard, and I was not expecting, for it to fruit. I just thought, and they have these big fruits now. But yesterday, a squirrel came and ate half of it, and it's just, I obviously don't want to kill the squirrel, but I want to scare them away for sure.
It was just long enough to break your heart, right?
Yes.
So let's talk through what Samrat was thinking about of this project. So first things first, there wasn't an existing rabbit model for him, but there is now because he put it in Roboflow universe. So if you have the same problem, you can just start from his North American cottontail bunny data set and model. But in his case, he wanted to collect some images of bunnies, and he taught me about the types of bunnies that appear in North America, so I can sound educated on this topic. He created a project. He began to do his annotations and pre-process it and augmented the data set. So augmentation is also a key thing with helping with active learning and underrepresentation, because you can generate more image examples programmatically, which is almost like, there's no such thing as a free lunch in machine learning, but this is pretty close for being able to generate more data very quickly. So for example, changing the brightness of images, changing the hue, changing the saturation, changing the zoom level so things could be nearer or further. Created a data set, had a model that was live, and then deployed it to his Raspberry Pi. And this project is fully open source. So if you want to deploy to your Raspberry Pi, you can do exactly the same process. Now, the active learning component. So what we were curious in doing, what Samrat was curious in doing, was uploading an image back to his source data set, which he has stored in Roboflow, via the upload API when there were conditions that he was sampling that looked like he needed to add that additional data set. So all the code here is open source, of grabbing an annotation, parsing the annotation, and uploading it back to Roboflow. And the key thing to think about here is, again, when do I want to sample from my inference condition? In this case, we might want to randomly grab an image maybe once a minute, once every 10 minutes, just to have data of the background of the lawn when rabbits aren't present. And then we probably want to initially build a model where the confidence is very low, and then getting those images back into our data set. Because you can imagine maybe Samrat has a dog or something that comes into view, and the model thinks that is actually what a rabbit might be. And so we want to collect those examples as well, so that over time we can fine tune and improve the model.
So
And in,
Joseph, so just so people, after this webinar, they are able to go and Google some of these things also. Could you explain some of the, sampling techniques, what are the names people use for these techniques in active learning?
Yeah, there's pool-based sampling and query-based sampling are both very common techniques.
Yeah.
In the post, which I think we'll make sure to distribute, we actually walk through these in a bit greater depth, where you have the full pool, or if you do like a stream-based approach, where you look as the images come through, you compare and say, do I want this image? Do I not want this image? And basically, like, the core question is, do you compute whether or not you want a given image in advance across the full like corpus of images, or do you do it kind of like image by image? And in the case of having small data sets, usually going image by image is pretty low compute. So it makes a lot of sense to do the full pool-based approach, where we take the full set of images that we've collected from our production conditions, run them all through the model, and then grab the ones that are lowest confidence and focus on those ones. Thank you for calling that out.
It's about 9:53. We should probably do our giveaway.
Yeah, I was going to say, this is sort of the end of the road here of everything from deploying to production and then making sure things were live. So
yeah, Phil, could you please share this URL also with our audience?
Yes, absolutely. And we'll that'll be on the YouTube video as well, which will be available Monday morning. So yes, thanks, Joseph. Really appreciate it. I feel like, every time you're on here, I learn something, and that's awesome. I hope that's true for the audience as well. So I'm going to ask a trivia question now. The first person to answer this question correctly on my screen will win. Joseph, would you like to tell them what they'll win?
yes, let me just pull up. I'll pull up the example.
Excellent.
So if you build with Roboflow, you know that you get access to, you guessed it, a special raccoon shirt. So we actually contracted an artist via an organization called Black Art House. And that artist has an awesome style that kind of makes this like exploding flower look. And they made this raccoon that's almost like a peace sign, like raccoon, and it's sort of like exploding outside of its like bounding box frame. And we only allow users that have built amazing projects or done OpenCV trivia correctly the ability to get these. So they are pretty exclusive and pretty cool too. So this is what's on the line here.
That's great. And from OpenCV side, we'll also throw in whatever the small mighty thing we have in the box, but you'll have to wait for it because we'll do a Kickstarter campaign on September 15th. And so it takes some time to get that, but we'll keep your name, in our set of people who will receive the free ones.
Absolutely. So you'll type your answer, everybody out there, type your answer into the chat window here. Just make sure that you're set to either everyone or hosts and panelists, so I actually see it, because if I don't see it, you can't win. So earlier in the webinar, Joseph used a model to find raccoons. That model was a specific version of that model. Which version was it? All right, looks like we got Philip Ha here. V40 is what I saw. Is that correct, Joseph?
That is correct. Yeah, we've trained a lot of raccoon models. We're up to 40.
I had to get clever with this one. Y'all have been so on the spot with the trivia answers. Finally, I stumped you for almost a full second. So
yeah, this is the one that I actually did not know the answer. This is the first one. I was stumped myself.
Nice. I even stumped Satya this time. I appreciate that. I think we have time for one. Do we have time for one question here? It's 9:56. Rajan asked, does Roboflow work with live video?
Absolutely. Yeah. So in the rabbit example, that was streaming live video. So that's a very quick question. I can say yes, And I'll even drop a link to a open source repo we have of doing video inference in the chat, and we can hopefully do another question.
Excellent. Yeah. Do you have any suggestions? Bruno asked, do you have any suggestions for using this active learning style in an edge environment?
Absolutely. So the difference with the edge environment is there's not going to be likely internet connectivity. And so the key thing is when you're running the model live, you're still going to get live confidence levels just running locally on the device. And you can still set a confidence threshold you're interested in requiring for your model. Then if you ever see a frame that comes through from your live feed in your edge environment, you can save that image locally to that device and cache it. And then the recommendation would be that on some periodic basis, you would either visit those edge devices or have it internet connected, maybe once every 30 days or something like this. Depends on the feasibility and the context in which we're working. And then send those back to a main source data set is one way by which edge active learning works well.
And I mean, realistically, you could even just go pick up an SD card and, upload it, retrain a new model, just manually bring it back out into the field if you're really old school. So Joseph, if people want to reach out to you and they have more questions, what are the best ways to get those answers from you?
We will, a few ways. One is we have Roboflow YouTube, Roboflow blog with tons of answers already that I'll encourage folks to take a look. And then they can email me directly if you have questions, and I'll make sure myself or a member of my team is able to help out. My email is joseph.nelson@roboflow.com. So feel free to email me with questions or thoughts, or maybe you want to get started with Roboflow, all that sort of stuff. Our team is eager to help.
Really appreciate that, Joseph. Thanks again for joining us here. Satya, would you like to take us home?
Yeah, thank you so much, Joseph, for joining us. I have two announcements before we leave. First is, September 15th, we are going to announce, what's in the box. If you go, please sign up for at the page that Phil had shared before, because we are going to give away 69 free small mighty things in the box for free. It would be a raffle and we'll give away 69 of those. And secondly, OpenCV for beginners course, the price is going to rise on September 1st. So that's something, if you're planning to buy it, now is the time. Again, Joseph, thank you so much. Your webinars are always informative, and it's a ton of help to all our audience. And Phil, thanks for putting this together.
Yeah, and thanks. Thank you, Satya, and thanks for everybody for joining us again. We'll be back next week, same bat time, same bat channel, 9 a.m. Thursday. We'll see you then.
Thank you, guys. Bye.
Thanks all.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Visit opencv.org/courses to learn from the experts. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.